Okay, so today we're doing, this unit that we're doing is really about polynomials. It's about polynomials. And it's about the solving equations, simplifying expressions, not really the functions and the graphing yet. I think we're going to do all that in one unit after this, where we do all the functions, including quadratic functions, which are polynomials too. But this unit is all about the polynomial expressions and equations. You can see on the slide when I expect we'll have a quiz on Friday, and that'll be about properties of exponents, the thing that we did last time, and the test on the 28th. So now you don't need, I put a slide up here like this, you don't need to copy every last detail of this. Unfortunately, I think some of you think that if you just copy every note and do every homework, that means you're going to get a good grade. And it's actually doesn't make any difference. You know, you got to understand. That's what makes you get a good grade. No substitute for understanding what we're doing. And sometimes copying for the sake of copying, when you know darn well you're not even going to look back on it. And doing the copying maybe distracts you from thinking about what we're doing in here. It may not help. Especially when you see this is a graphic that is copied right out of the book. If you want to see it, go and look, chapter 5. You'll find the exact thing. Okay, but this is only intended to be, this is the vocabulary of talking about polynomials. Right? Polynomials are classified by their degree, which means the highest power of x, and by the number of terms. So when we say something like, this is a cubic trinomial, we know what we're talking about, right? So when it comes to the number of terms, then one term is monomial, 2 terms is binomial, 3 terms is trinomial. We've already been using all of those words, right? If you have more than 3 terms, you just say polynomial. Poly means many, right? And it's actually a more general term because you could refer to binomial, trinomial, anything can be a polynomial, right? It's the most general term to use. But most of the time, we do say binomial, and we do say trinomial, and things like that. Now, when it comes to degree, degree is the highest power of x. And we know that, for example, linear means it's x to the first, and quadratic means it's x squared. Cubic is x to the third. There's actually a special word for a 4th degree polynomial that's called quartic. There's actually one for a 5th degree polynomial. What would you guess that it is? Say again? Quintic. Right? Quintic is for 5th degree, which is not in the chart. And when we get to the point of doing scatter plots with the calculator, we'll put in a bunch of data, we'll look to see what the shape is, and then we go to the menu of functions that we can use to approximate it. It actually has quartic in the menu. That's one of the options. So we need to know linear, quadratic, cubic, and quartic when we get into that menu. Now, a constant function, that is linear, right? But it's actually, if it was a straight line, it's a horizontal line. Function value is the same all the time. So a constant function is something like that. And, if you get confused by all these A's in here, just think of the subscript as just like saying this is a different constant, a different coefficient. A1 is different than A0. A2 is different than A1. In the calculator, they actually use the letters A, B, C, D like that. So if I was going to do a cubic, it'll say AX to the third plus BX squared plus CX plus D. So these little subscripts are just like a way to designate a different number. Somebody asked about that in the last class. So again, you have a constant function has a 0 degree because it has. I mean, this gets into the properties of exponents. Actually, we didn't go over that. The properties of exponents tell us that anything to the 0 power equals 1. So if you have x to the 0 power, you wouldn't write it in there anyways, right? So in this case, we have that's why a constant function is 0 degree. And linear function is 1st degree and all that. Quintic is 5th degree. If you get higher than that, you're just going to say 6th degree and 7th degree and 8th degree. Just use the number. There probably are words for it, but I don't know what they are. I've never seen them before. So what we're going to do today is add, subtract, multiply polynomials. That's it. So something to keep in mind. When we do all of those things, we always want to leave the answer in standard form. And by standard form, we mean no parentheses, highest degree term is on the left, right? And then descending order of powers. Right? So if it's a quintic, x to the fifth, and then x to the fourth, and then x to the third, and then x squared. In order, always. And the adding and subtracting of polynomials, I mean, it's just combining like terms. That's all you're doing. Good. So here's their examples of... Sure. Are you done? Okay, say so. If you have me stop, then say when you're done so I can keep going. I mean, in the end, I'll just make less notes. Okay. So adding or subtracting. They give it in two different formats. I'm not going to tell you which way to do things. Whichever way works for you is fine. You can see in their adding in what they're calling a vertical format. They're taking the two polynomials that they're adding, and they're lining up all of the like terms. Right? So they can just add straight up and down to combine like terms. Sounds easy enough? You like to do it that way? If you go in the horizontal format, now they're writing it all on the same line. And you notice that they actually, before they combine the like terms, they put them right next to each other. Right? They put them right next to each other so that then they combine them. And you don't really have to take that step. It's probably not what I would have done. I mean, I usually would just do something like this. If I have all those terms, I probably would have taken a step where I get rid of the parentheses. So it looks like this. 3y to the third minus 2y squared minus 7y plus. Actually, I would not even have written a plus, because plus and negative is minus anyways. Okay, and then I just identify the like terms. These are like terms. These are like terms. And then again, highest degree term to the left, so I write the 3y to the third. And then I combine negative 2y squared minus 4y squared minus 6y squared. Negative 7y plus 2y. And then there's a negative 5 that does not have a like term, so negative 5. So you could do anything you want. If you'd prefer to see them all lined up when you do that, then go ahead and do it. Knock yourself out. So I'm sure that's a you try. Get that? Should. Negative 6t squared minus 7t minus 6. So subtraction can be harder because if you're subtracting a polynomial and it's more than one term, you got to take into account that that means you're going to have a negative or a minus in front of parentheses. And what's that going to do to the sign of everything in that parentheses? It's going to flip it, right? So that's something extra to be careful about that you don't have to worry about when you add. So notice what they do here, right? They're still going to make this into an addition problem. They take that minus and they turn it into a plus, and then they flip the sign of everything so that they can be added up.
Is it everything on both sides?
What's that? The flipping?
It's just
what's being subtracted. Right? If you're subtracting this, actually it says you're subtracting this minus this. So that negative changes all of those into opposites. Right? So again, that's their vertical format. In the horizontal format, they still just have, you have to distribute that minus. Before you combine like terms, distribute the minus. And then, they're writing all the like terms next to each other. I probably wouldn't. I'd probably just say, okay, that's 4z squared minus 5z squared, negative z squared. 9z plus z, 10z. Negative 12 minus 3, negative 15. You need to be somewhat systematic, whatever way you have it works for you, but you need to be systematic and write neatly. Okay, that's me. So try one on your own. So then take a step, distribute the minus, and then combine like terms. Here's our like terms. Those are like terms, and these are like terms. So starting with the highest degree term first, 9d to the third minus 1d to the third. 13d squared. 8d. Negative 3 plus 4. Thank you. T plus 1. That looks better. Okay, which leads us to multiplying. So it's kind of like the multiplying. When we were multiplying complex numbers, some of this is similar. When you multiply two factors at a time, remember, the factors are going to be polynomials. They might have 1 term, 2 terms, 3 terms, many, many terms. Usually, they're going to have 1, 2, or 3 in this level of class. We're probably not doing much more than that. And it depends on what you've got for what method you'll use. If you're multiplying a trinomial by a monomial, 1 term, that's probably distributive. Right? If I'm multiplying 2 binomials, that's probably 4. Right? So in the end, you can use any of these methods, or you can do something that works for you. I'm going to show you a different way to do this than they show, because it's the way I've been teaching it the last 5 or 6 years anyways. And I did say in there, the multiply 2 factors at a time, because we will multiply more than 2 factors. So just like multiplying the complex numbers, first we have to start with 2 and then multiply that by a different factor. Same thing here. So multiply. So they're giving us 2 different formats here. Here's their vertical format. And they've written the 2 polynomials, again, lining up the like terms. And they really turn into, I've actually not seen it done quite this way, where it looks like you're multiplying. Let's call it long multiplication of numbers. Right? They got it all lined up. And now they start with the -2. -2 times -6, positive 12. -2 times 3y, -6y. -2 times -2y squared, positive 4y squared. And now, move over a space. Because we're going to be multiplying by a y, there's no way we'll be putting anything in the constant column. Right? So they move over 1 and then multiply everything times y. By doing that, they are making sure that everything is lined up. And then combine like terms. The second, what does it look like they've done in the horizontal? It looks like they're distributing. They're taking it in 2 steps. They're taking this x plus 3, and they're multiplying it times 3x squared and -2x and 4. And then they're distributing again to get from this line to this line. I think when I did this, when I was going through Algebra 2 or whatever many years ago, I was probably more or less you just got to make sure you're multiplying everything in one set of parentheses times everything in the other. And I was probably just not really having this line in there, but just going x times 3x squared, x times -2x, x times 4. 3 times 3x squared, 3 times -2x, 3 times 4. Just making them all combine like terms. That always seemed to work for me. But I'm going to show you a different way that you might find even better. Then these are the same 2 problems that were on that slide. But I had a student who was a military brat, and he had been in Heidelberg, Germany, and his teacher over there, I assume in the Tabb system, had shown him this way. And at the time, he presented it in front of the class, and everybody said, "Oh yeah, I like that." And so after I would ask, I would show him and say, "Would you like to do it like that?" And everybody always said yes. So we did. But honestly, you can do it whatever way you want. But just try to be systematic and make sure you're multiplying everything in one set of parentheses and everything in the other. So this is what he showed me. And you might have seen this before. If you haven't, then be news for you too. Okay, so let me I'm going to do the first one. So we made ourselves a little grid. And I'm making it a 2x3 grid because I've got a binomial times a trinomial. Okay, now I could make the column what's on the top and what's on the side. I could switch it. It doesn't make any difference. But, I'm going to put the binomial y minus 2 goes here. And the trinomial -2y squared plus 3y minus 6 on the top. And now I'm going to fill in the grid by multiplying Like if I want to fill that square, then I'll multiply what's at the left and what's on the top, and I'll put the result there. So fill in all 6 blocks. So the first one is negative y times negative 2y squared is what? Negative 2y to the third, right? Because this is properties of exponents, right? When you multiply y squared times a y, you get a y to the third. So this is negative 2y to the third. And y times 3y, 3y squared. And y times negative 6, negative 6x. And negative 2 times negative 2y squared. Oh, I made a mistake. Should have been a y. Okay, and negative 2 times negative 2y squared, positive 4y squared. And negative 2 times 3y, negative 6y. And negative 2 times negative 6, 12. All right, so we still have to combine the like terms, but we've made all the terms. You know, this makes sure we multiplied everything in one set of parentheses times everything in the other. And normally the like terms will be on the diagonal. Right? There's the squared terms. There's the y to the first terms. So I'm going to start with negative 2y to the third. That didn't have any other like terms. And now what's 4y squared plus 3y squared? 7y squared. And negative 6y plus negative 6y. Negative 12y and 12. So if you find that useful, you can use that. I would call that using a grid. So try those two. In any way you want, try those two. So here we go. So you can check your work. You like that? How do you do? Get it? Tabb? Get it? Super? John? Not that hard? What did you call it?
We called it a lattice method.
The lattice, okay. What's a lattice? Quiet, please.
It's kind of I know. That's what I'm trying to think. I put it like under my deck where it covers.
Yeah, but it has kind of a frame to it, right? Yeah. So I guess you could think of the grid as kind of like that.
I can look it up.
Okay, quiet. Peter. Stop. Okay. So next is we got to learn how do you multiply 3 factors together. And they're actually kind of nice because they're all binomials. But again, kind of like multiplying complex numbers. You got to take 2 of them and multiply them, and then multiply the rest or the other factor. So, and you could pick any 2. You know, sometimes it makes sense to do particular 2, right? Based on a pattern you might see. These here, I don't think so. I mean, does anybody have any preference which 2 would be the easiest to multiply? Maybe the 2 that are just all positive? I mean, let's say that I start with these 2. Right? That would be x squared plus 3x plus 1x plus 3, which is x squared plus 4x plus 3. And at that point, we still have to multiply by the x minus 5. So now it turns into the same kind of problem that we were just doing. So you could pick any method you want. Again, I'm probably going to use the lattice method. Right, x minus 5, x squared, 4x, and 3. Okay, now I'm going to fill up the grid. X to the third, plus 4x squared plus 3x minus 5x squared minus 20x minus 15. So combine like terms, x to the third. How many x squareds is that? Negative 5 plus 4. And negative 20x plus 3x. There we go. So, try the next one. I'm sure it's one for you. Check my math. Could be having this on. What's that? Is that what you got? Okay. I'm sorry. Is that right, Michelle? So the main thing is, if you got more than 2 factors, you're going to have to multiply 2 at a time. That's all you can do. Now the next thing that's in here is you might recognize some special, what do they call them? Patterns. Special product patterns. And honestly, what is this? This is just like the opposite of factoring. I mean, if you had to multiply x plus 4 times x minus 4, you might say, hey, wait a minute, isn't that just how we factor the difference of squares? Wouldn't that have just been the factoring of x squared minus 16? Yeah, that's it. So you would just jump to the x squared minus 16. The perfect square trinomials. Right? If I had to multiply y plus 3 squared, I know that it should be the first term squared, the last term squared, and 2 times y times 3, which is 6y. Right? I just follow the pattern, if I know the pattern. And this can come in handy. For example, what if I had to multiply 3 factors, right? Like we did on the last slide. And 2 of them were, x minus 2 times x plus 2 times x minus 7, let's say. You know, if you're asked, which 2 do you want to multiply first, you would absolutely say, let's do the x minus 2 times x plus 2, because that's the factoring of a difference of squares. I would just immediately go to x squared minus 4 times x minus 7. So recognizing the special pattern, it might help you out. Now, the cube of a binomial at the bottom, I find this a little out of place. But I don't think most of us would recognize right away, like memorizing a formula like that. There's a place where this comes up in math analysis, where after you've done a lot of other things that involve factorials and things like that, then you come up with this thing that's called the binomial theorem. And that's where something like this comes out, where you learn how to raise a binomial to a power and the pattern that it produces. I doubt we would have to do much of that. When I first saw this, I thought it was something different than it was. And we're going to get to that in a couple days. So we have to factor the sum and difference of cubes, kind of like the difference of squares. Well, with cubes, we've got a sum and a difference. And it has a pattern, not that pattern. So I'm going to skip over I think the one that you try actually had everything to do with that. So let's just skip over. No, these are their examples. Sometimes I think when you see it all written like that, you don't quite get that. They're saying this was the problem. You don't see the rest of it. They were just saying, multiply these 2 binomials. Okay, and then if you write, oh, that's the difference of squares. Minus 2 squared minus 16. Done. Or, oh, that's going to be the a binomial squared, that's got a pattern. The first one squared, the last one squared, and 2 times the first times the last. And I'm going to skip over that. Honestly, I think that if you got to that point there, I would probably just FOIL xy minus 4 times xy minus 4, and then multiply that by xy minus 4. Okay, spot the errors. Find the errors. What's the error on the left? They didn't flip with which size? Okay, up here?
Yes.
Yeah, I mean, they get that leading term. They get that to be the negative s to the third. But that should have made that a minus and should have made that a false negative. And that's a great example, because that's the thing we always make a mistake on. And then what did they do wrong here? You know, like I just kind of downplayed the, you know, the cube of a binomial kind of thing. But here's the thing to keep in mind. There was a formula for when you cube a binomial. How many terms was it in the expansion of that? Was it just 2 terms? No, it wasn't, right? So it looks like, if we look at the special pattern again, you know, look at the bottom there. Both of those, whether it was a plus b or a minus b, there was 4 terms on the right. What does it look like they did in this error? They just cubed the first term and the last term. They didn't do the other 2 terms. Which, by the way, we tend to do that a lot. Even we'll get like x plus 2 squared. A lot of students will write x squared plus 4, and they forget about the middle term. So that is it. Now, next class, I think we're going to do divide. And divide is much different, and there's much more to it.